Okay, it's 8:30, so let's begin. So today, hopefully we'll finish up logistic regression. Also, just a reminder, project number 3 is due today at 5 p.m. Also, remember that number 4 and number 5 on the project for the logistic regression part, you do not need to do. Are there any questions? Okay, first thing I want to talk about, though, is briefly discuss course evaluations. So I would imagine sometime this week you will be getting an email saying that course evaluations are available to you on Canvas, and probably starting on maybe Sunday, maybe Monday, you can start filling out course evaluations. And they're located in the usual spot on Canvas. And I just want to emphasize that, you know, these evaluations are actually very important. Unfortunately, for my department, it's the only way that my teaching can be actually evaluated, which is too bad. And you know, don't just decide, I'm not going to do it at all because it's not important. It truly is. So once these evaluations are available, make sure you take the time to complete them. It probably takes 5 minutes to do. And in these evaluations, it can be easy to focus on negative things, but make sure you also talk about positive things that you do like about the class. If you like these notes that I've provided to you, the R programs, the videos that I make available, the course website, make sure that you say those things, because if you say them, then that can encourage other faculty to also incorporate them into their own courses. Now, there is actually a second evaluation that I've put together. There's some additional questions that I've created. And this second evaluation, it is required for you to do. And it's under quizzes, course assessment, quiz survey. Okay? So if you just take this survey, you'll have a number of questions. Now, do note that you see points here listed with each question. Those aren't the correct points. For some reason, I am unable to remove those points. Simply, if you do question number 1 on the quiz, you get 5 points. And the whole quiz is worth 5 points, so you get a perfect score. If you just do number 1. Number 1 says, I will be answering the remaining questions. Yes or no. So I'm giving you an opportunity to say, okay, yeah, I don't feel comfortable doing this quiz. I'm going to put no. That's fine. But if you say yes, you can continue the quiz. Now do note, and I didn't have it up there, I have actually turned the quiz on to be anonymous. So I don't know who's saying what. If you do question 1, you earn 5 points. Now, hopefully, you will continue doing the rest of the problems, or rest of the questions on the quiz. And simply, here are the questions. What grade do you expect to earn in this course? What grade would you actually give the course itself in terms of what you think about the overall content of the course? What grade would you give me as an instructor? And then we have some other questions that can be very helpful to me. What were some aspects of the course that you think would be good to continue for future semesters? Now, in this question and some of the other questions that you'll see here, it's okay to repeat yourself in terms of what you said on the other standard UNL course evaluation. But what are some things that you want me to continue in this course for future implementations of it? What were some aspects of the course that you think could be improved upon for future semesters? I really like teaching, and I'm doing this because I want to help you learn this material. And so if you think there's something else that I could do better, or do that I'm not doing at all, let me know. Then we have a long question here. So I've taught this course 2 different ways in the past. I've taught it using the format that we've seen here. I've also taught it using a blended/hybrid learning format. And in fact, that's what I usually use in most of my classes right now. I decided I wanted to go back to this more of a traditional format this semester. So I wanted to, well, I won't get into the reasons why. So I don't want to bias you in terms of your answer here. And the purpose of this question is to describe to you how I could have taught the course differently. And for you to choose which would you prefer, the format that we have or a blended learning format. So here's how the blended learning format would work. Prior to our Tuesday class that starts off the week, I would have you watch about an hour and a half of videos that I would put on my YouTube channel that basically has me going through the content very similar to what I do in our normal class time. So essentially, it takes what we do here in our class and transfers it to a video format that you watch beforehand. You know, obviously at your leisure, but you do need to watch them before the Tuesday class. If you want to see some examples of what this looks like, here it is from my Stat 875 course. We would primarily meet for this class just on Tuesdays. And in the classroom on Tuesdays, we would start off with a question and answer session, where if you have questions about what you saw in the video in terms of the material, I will hopefully have answers for your questions in class. Then for the remainder of the class, basically what we will do is I would go over material that I know from my past experience that students sometimes have problems with. I would also have additional data examples that we would go through. And also we would spend more time talking about the projects and also talking about the tests. That's what our Tuesdays classes would look like. The key is no new statistical methods would be actually introduced during this Tuesday class time. Then, on Wednesdays, due like at 5 p.m., you would have a low-stakes quiz that you would need to complete by Wednesday 5 p.m. Very similar to those 4 quizzes that you had at the very beginning of the semester. It will be 5 questions. Each question is worth a point. And you will need to complete these quizzes weekly. These quizzes will be over the corresponding material that was in the videos and also what was also reinforced during the Tuesday class. Then on Thursdays, we would actually meet in person just 3 times. And those would be our test days. The remaining Thursdays of what we would do for our course is simply I would just make it an office hour session where I would be available here maybe in person, or we could just do it only on Zoom. And so that if you need some individual help, this is the time for that. So that's an alternative blended learning format for the course. And I just simply want your opinion. Which would you prefer? What we did this semester or the blended format? Okay? Question 8. Well, if you'd like to provide maybe some additional comments regarding what I just said about the blended learning format there or your current format, please enter your comments here. And then lastly, I'm interested in knowing how much you use then these recordings, these videos that I've created of our classes. How much do you use them? So approximately how many minutes of the recorded class videos did you watch during the course? I know that's going to be difficult to approximate well, but just do your best. So for example, a value of 750 means 750 minutes, which would be 10 whole class periods. In total, we will have about 1,950 minutes of recorded videos by the end of the semester. Okay, so once you're done with that, obviously click on Submit, and then you're done. Any questions about this additional course assessment? Okay. So this is due. Let me back out of this. December 6th at 5 p.m. Okay, so please make sure you get it done by then. And again, it is worth 5 points just to complete that problem number 1. Okay. So we've been talking about logistic regression. Briefly, let's review. We have two main ways that we can write out our model. One way is on the left-hand side, we'll put pi, which is like our probability of success. Probability y is equal to 1. It's equal to e raised to a linear combination of the betas with the x's over 1 plus e raised to the linear combination of betas and the x's. If we do some math, we could just rewrite it so that we only have this linear combination on the right side, and on the left side we have the log of pi over 1 minus pi. This transformation of pi there is called the logit transformation, so we could also just call it logit of pi. Then using this kind of a model, and then we obviously estimate it to a data set, so we get pi hats, beta hats out. We would predict a particular observation or maybe a new placescape, for example. We would predict y is equal to 1 if pi hat is greater than a cutoff probability. Could be 0.5, but it could be something else. Otherwise, if pi hat is less than this cutoff probability, we would predict y is equal to 0. So that's how we use this to predict the grouping or predict the classification of a particular observation or new occurrence. Now we started talking about, we spent some time last time talking about, how good is this model doing in predicting? And we have two main measures of goodness, the sensitivity and the specificity. Both of them are conditional probabilities. So given we actually have a positive, what's the probability that we predict positive? That's the sensitivity. Specificity, given it's actually a negative, what's the probability we predict negative? Then with these two accuracy measures, we could basically look at the complements with them, and we can look at a false positive rate, which would be just simply the probability predict positive given its actual negative. So we made an error. How often does that happen? We also have the false negative rate, probability predict negative given it's actually a positive. Okay. So with that then, we would like to be able to use the sensitivity and the specificity to figure out what should I use for a cutoff probability. And the way that we can do that is with what are called receiver operating characteristic curves, or ROC curves. These curves were first developed during World War II, where the Allies were using it with respect to, they developed some new radar technology to detect airplanes, for example. And they were using that to determine, was this thing on the radar, was it a false positive or whatever? Okay? And so that's where they were first developed. Now, what the receiver operating characteristic curve is you plot on your y-axis the sensitivity for various cutoff probabilities. So, let's say I have a cutoff probability of 0.05. Let's find the corresponding sensitivity. Suppose I have a cutoff probability of 0.1. Let's find the sensitivity. And we plot that versus 1 minus the specificity, which is the false positive rate. So notice both of them, sensitivity and 1 minus specificity, when you look at that conditional probability, always have predict positive on that, I guess, the left part of that probability. So we're comparing two different conditional probabilities in terms of the predict positive, where on the y-axis we say we predict positive given it's actually a positive. On the x-axis we're going to put predict positive given actually negative. We figure these things for a bunch of different cutoff probabilities, and we just plot them, and we end up plotting them as a curve. So to see how this works, I have it's a older paper, but it's really the best one I've ever seen that describes these ROC curves. This paper, we'll call it paper, comes from Scientific American magazine. So this is a magazine that's been around for at least 100 years, maybe 150 years. And what they do is that they publish articles about science, but written at a level that pretty much anybody can understand. And so there was this nice article 20 years ago that talked about these ROC curves. And you can download this corresponding article from my course website under section materials. You're not required to read it, but I encourage you to read it. And we are going to focus here on class on one specific part of the article. I'm going to make this a little bit bigger. Actually, that's too big. There we go. And on the left side there, you see an ROC curve. And this example that they talk about in the paper talks about glaucoma diagnoses, where you can imagine a situation where, let's say the probability of success is, oh, you have glaucoma. And you might remember going to an eye doctor, and the eye doctor takes it like a pressure reading with your eye. They blow like a puff of air into your eye, and they use that to get a pressure reading. And so in this kind of a situation, one could actually look at a logistic regression model such as this. In the end, the higher the pressure, the higher the probability of having glaucoma. Now that's what ends up happening. And using a bunch of different cutoff probabilities, one can find what's the sensitivity, what's the 1 minus specificity of a corresponding diagnosis, or the corresponding method here, I should say. Okay? And focus on, well, let's just do this. So on my y-axis, we have the sensitivity, which they call the true positive probability. The y-axis, we have 1 minus the specificity, which would be the false positive rate. Okay. Now notice we have this straight line here. Bisects the origin of the plot. And it's called the line for chance accuracy. What does that mean? Well, let's take a point here on this line. So that corresponds to a sensitivity of 0.3. Right over here. Actually, I want to do it this way. I didn't write this out the best. Hopefully you can read my handwriting. So we have the sensitivity, probability you predict positive, or I said positive predict. Probability you predict positive given true positive. Let's say that was 0.3. 1 minus the specificity, which is the false positive rate. Let's say that is the probability that you predict positive given true negative. That's also 0.3. So notice they're equal. So notice what this says is that your probability of predicting a positive is exactly the same. And so it's almost like flipping a coin. That when I make that prediction, half the time it's going to be positive, half the time it's going to be negative in terms of the truth. Okay? If I come up here, .8 and .8, I have the same thing happening. We don't want that to occur, actually. We don't want to be on that line. because your probability that you're going to predict something's positive is always the same, whether given as actually a true negative or it's a true positive. Any kind of diagnostic method like that is not really worthwhile. Instead, what we want to do is be in a situation like this. Suppose I go again from point 3, I project up to there. Now in this particular situation, I have that. So, given it's a true positive, the probability that I got it right is now 0.8. Given it's a true negative, the probability I predict positive is only 0.3. This is a more ideal situation than what we just saw on that line that's called the line of chance accuracy. And so, what's actually being demonstrated here is actually two different ROC curves. You could say one's actually a straight line. And we want to have a situation like this. Look at another situation. Suppose I'm at 0.8 here. I come all the way up to there. Now my sensitivity is about 1. But my false positive rate is about 0.8. It's still better than having 0.8 and 0.8. But, you're having a high, to have such a high sensitivity, you're giving up a lot with respect to that false positive rate. Okay. Take a look at my notes to make sure I'm talking about everything that I want to. Now, once again, how is, let's say, this curve here being formed? Well, perhaps a cutoff probability of 0.05 is used, and a point is drawn on it, corresponding to that sensitivity, that 1 minus specificity. Then we go to a cutoff probability of 0.1. Perhaps I'm right there. 0.15. Perhaps I'm right there. That's how this curve is actually being formed. Okay. So, what one does is looks at this curve here. And the one that's actually labeled as ROC curve for eye pressure. One looks at that curve. And one decides, okay, what sensitivity do I want? And then also simultaneously think about what false positive rate can I live with? Maybe I can't live with much of a false probability rate, and I would prefer to be here instead. Or maybe I can live with a high false positive rate. Maybe, if someone's, let's say, diagnosed with glaucoma, maybe there's going to be some other follow-up test that's going to be done. In that particular case, then I could probably live up there. Once you find where you want to be on that curve for this diagnostic method, this prediction method that you're developing, then you can go back, you can say, into the curve. I'll show you how to do this, to figure out what exactly was that cutoff probability that gave me this sensitivity, that gave me this false positive rate. That's how these ROC curves are used in practice. And you can see, especially for like medical diagnoses, these are widely used. This one? What's your question about? I'm sorry? Okay, so in this particular case, let's say I really want to have a high sensitivity. Okay? Now I know for this diagnostic method, for this, let's say, logistic regression model that I'm using, if I have such a high sensitivity, I'm going to have to live with a high false positive rate as well. When would this maybe be appropriate in actual practice? Let's say that this particular test is run and someone's diagnosed as having glaucoma. Then, and I don't know if this is a fact for this particular disease, perhaps some kind of follow-up tests would be automatically implemented after that. That maybe would have, let's say, a much lower false positive rate. That would, let's say, confirm that indeed a person does have glaucoma. Does that help you? Okay. Now I have a question for you. Let me come back to that plot and do a little bit of erasing. Let's say I have some other kind of diagnostic method that uses maybe a logistic regression model. And I have a curve that looks like this. Okay? Which curve would you prefer? The red one or what looks to be a purple one? What? The red one, yeah. Okay? Because you're going to be giving up less in terms of those false positives when you have a high sensitivity. So I've actually given a question on a test before in this class. I say, well, show me what would be the most ideal curve to have. Now, this is not on this particular test. Okay, that would be the most ideal. You know, it's a good question because it makes sure that students understand, well, how would this be used in practice? Now, also, you can see in these particular situations that, let me do this. I could actually find the area underneath this curve, right? So that's the area, roughly, underneath the purple curve. Which is going to have a higher area, the red curve or the purple curve? The red curve. And so what people often use as another method just overall to say, well, is this the better method for prediction or is this the better method of prediction? They'll look at the area underneath the curve in this, so you could say unit square that we have here. Another thing that I want to point out. Notice we have a second a y-axis and a second x-axis. And perhaps when I first introduced this, you might be thinking, well, what if we were interested in looking at the specificity versus the 1 minus the sensitivity instead? Well, because of the relationships between the false positive rate and the specificity, look at this. Here's the specificity on this second x-axis. So remember, it's just going to be 1 minus what was on the x-axis. Also, here's the 1 minus the sensitivity, or in other words, the false negative rate, as the second y-axis, because it's just 1 minus what was on the first y-axis. And so you do get it all on this kind of a plot. That's kind of cool. Okay, so let's take a look at the place kicking example now. Now I have to admit that doing these plots in R, I wish they were a little bit easier. There are a number of packages out there that allow you to do them. The one that we're going to be looking at, I think, is a good one to use for a classroom situation. So that's what I use. That's what I use for it. There's going to be, I think, like 4 different steps that we have to use in order to actually get the actual plot. So I'll try to label them as we go along here. Also, what complicates things is the actual syntax that's being used. So the package that we're going to use is called ROCR. That name sounds or makes sense. ROC for R. And to begin with here, so step 1, we'll call that step 1. Get pi hat. And we've already done this before. So for example, we've used the predict function to find the pi hats for our data set itself. Let me just show you. There we go. So this is how we got the pi hats from before. So that's step one. Step two. Now we use a function from the ROCR package called prediction, where the first argument is predictions, where you put in your pi hat. And for the labels argument, you put in the true, let's say, y's. So the ninth column of placekick was the good variable. So what this is going to do is going to calculate number of false positives, number of false negatives for a bunch of different cutoff probabilities. That's what this is doing. You can see, okay, well, that's some of the stuff that I'm going to probably kind of need for one of these ROC curves. Now, what makes things complicated is this. Let me execute the code. Now, you might be wondering, okay, well, what's actually inside of this object that I returned called save.pred? And we've talked about that. Well, if it was a list, I could say save.pred or name save.pred. And I get null. There's actually stuff in there, though. So, it's going to take me a few minutes to discuss why this is occurring. We're going to go back in time. We're going to go back to the middle 1970s at AT&T Bell Labs. This is where a statistical programming language called S was developed. The reason why it's called S for statistics. Okay. This language was developed, and then by the 1980s, it was actually licensed to a company that actually created a commercial software package that people had to buy. The package was called S+. There was a number of different versions of S, like S version 1, S version 2, S version 3. By the 1990s, S version 3 was very prominent. But in order to use S version 3, you had to purchase S+. Then in the early 1990s, mid-1990s, two researchers at the University of Auckland, in New Zealand, they decided to create their own statistical software package that was based upon the same syntax as what was in the S language. And do note that you can't, let's say, copyright a actual programming language. And so they decided to create their own that would basically mimic what S did, but they wanted to make it free. They called their language R. The reason why they called it R, well, because we already had S. So that kind of makes sense. Two letters right next to each other. And also these two individuals, their first names both began with the letter R. So R was based upon S version 3. It was fully released February 29th of 2000. Now, in the late 1990s, these Bell Labs people also then created a version 4 of S, called S4. And eventually that was incorporated into R as well. It never quite took hold as much as S version 3 did. So S version 3 is still what R is predominantly based upon, but you do see some packages that are written using the S version 4 syntax. And this is one of them, this ROCR package. There are some small advantages of S version 4. I never have felt that was big enough for me to use that in my own work, so I typically only use S version 3. But in order for us to be able to use this package fully, we have to understand basically one small difference between S version 3 and S version 4. And that is, rather than using names, so we used names before to see what are called the components of a list. Save.pred is still a list. It's just in the S version 4 syntax, and so we have to actually use the components in the list are called slots, just a different name. And so to see what those slots are, we have to use slot names. Okay? So if I say slot names, then I get what I'm used to seeing when I usually say names. And we can see we have a number of different things here, such as cutoffs. So for a bunch of the calculations that are being done, a whole bunch of cutoff probabilities are used. And if I want to see the cutoffs, I can take this slot. Or I can look at this slot. FP stands for false positives. FN corresponds to false negatives. TP, true positives. TN, true negatives. And all these false positives and false negatives and all those correspond to a particular cutoff in cutoffs. So if we look at the very first, well, let me say this first. So if I want to access now stuff that's in this list, rather than using the $ to actually access it, I use the @ symbol instead. That's it. Okay. So if I say save.pred at FP, for each of the cutoff probabilities that are actually in the cutoff slot, here are the actual corresponding number of false positives. Well, what are those cutoffs? Well, I just say cutoffs, and you're going to get a vector of the same length. Okay? Now, the way that this is constructed, notice at the very beginning, we have that right there. Let me explain what that is and relate it to something that you've seen before. So remember, I've actually estimated my model. So it's in mod.fit. It's a list. This is actually an S version 3 syntax. And so if I want to access part of what's in there, like mod.fit $coefficients, I can just do it like that. Here's another way that I did not teach you before. Two square brackets on the left, two square brackets on the right. The one says, I want the first component of the list. Okay? So that's another way to access it. You know, look at if I did, let's just do 11. Okay? I get something else. Now, this save.pred at FP is actually a list as well, and it only has one part of the list, and it's just labeled as 1. It doesn't actually have a regular name. And so if I want to access the individual elements, I have to put the square brackets there, and there I go. It's a lot of syntax here. Remember, use my code as a template for your own code. That's a great way to first learn how to do this stuff. This is the only time that we're going to be using S version 4 this semester, so that's why I'm just giving just enough information for you to understand what's going on. Okay. So I can look at my false positives, corresponding to particular cutoff probabilities. Here are the cutoff probabilities listed here. Okay? So that's step 2. Find a bunch of false positives, find the false positive, find the false negatives corresponding to cutoff probabilities. Or you say true positives, true negatives as well. Step 3 of the process to finally get to the ROC curve, step 3 or 4, is I have to use a function called performance, where I say I want to take the stuff that I just formed in save.pred, and what I want to do is take that and calculate my sensitivity and my false positive rate. Of course, that's what's going to be on our ROC curve. So, if you look at the help for this performance function, you're going to see a number of different, let's say, keywords out there corresponding to measures that you want to do. So, measure corresponds to what we're going to put on the y-axis. X.measure corresponds to what we're going to put on the x-axis. Now, you might be wondering, why don't we call this y.measure? Well, you could use the performance function itself for stuff that's not stuff that you're going to graph. Like, for example, the area underneath the curve. This function will give this to us. In that case, we're not necessarily graphing. I just want the area. Again, I can look at slot names with this and look what we get here. So, for example, we get the actual values that are going to be on the x-axis, the actual values that are going to be on the y-axis, and this alpha dot values, even though it's called that, which is kind of weird, is going to be our cutoff probabilities. And I think they were just trying to be general because you could use this function to produce a whole bunch of stuff. And so how about we just call them alpha dot values, for lack of a better name. And then finally, step 4, we use the plot function. There is actually a specific method plot function inside this package. So if I say plot, and just put it as the first argument, save.perf, it will do what we want it to do. Put what we want on the y-axis, what we want on the x-axis. And then I can put a title on the plot, and for some reason the authors of this function did not allow one to use, let's say, the panel.first argument to exist, so you could put grid lines on the plot. So if you just, outside of this function, just put grid lines will be drawn. It's not, when you do plots, typically you want to have the grid lines behind the stuff that you want to plot. Here, this will essentially be in front of it, but it's really hard to see that that actually occurs. And so this is what we get. So here's my ROC curve for the place-kicking data set. So we can see sensitivity. We can see false positive rate right there. So for example, if I have a false positive rate of 0.2, that's going to correspond to a sensitivity about 0.77 about. If I allow for a false positive rate of 0.8, I will have a sensitivity of about 0.98. So an actual application then, what you would do is look at this plot and decide where am I most comfortable with, or what I would say for a particular sensitivity, what false positive rate could I live with? And then that would, perhaps it might be, let's say, right here. Then, as I will show you shortly, you go back and figure out what that corresponding cutoff probability would be. Now, in this place-kicking data set, it's kind of hard to make that decision, okay? Can I live with a false positive rate of 0.8 so that I can predict all my kicks almost all the time correctly in terms of given it's a true positive? If we had a medical application, I think it would be much easier to think about, to talk about the trade-off between false positive and sensitivity, and think of it in terms of humans and trying to diagnose them with diseases. Okay, let's see here. So how can I get now this cutoff probability? Let me jump on over here to my program. It's not as easy as you would hope it would be. I will tell you that to begin with. First, I'm going to do some renaming of stuff to hopefully make it easier for you to see what we're doing. So, remember the x values of save.perf was 1 minus the specificity. In other words, the false positive rate. So I'm just going to simply take those out and put them in an object called 1.minus.spec. Also, those y values in save.perf was the sensitivity. So I'm going to take those out, create an object called sense for sensitivity. And lastly, the corresponding cutoff probabilities are in alpha.values. I'm going to take those out and call them cutoff. Okay. So again, here's cutoff. All those cutoff probabilities. Next, I want to, let's say, suppose if I look at my plot here, let's say that I can live with a false positive rate of 0.5. This will give me a sensitivity of about 0.9. I'm going to find that cutoff probability. So what I can do is as follows. Suppose I look at, in terms of all my 1 minus specificities, I look at, well, which ones are greater than 0.495? My goal is to find the 1 minus specificity of 0.5. I look at all of them that are greater than 0.495, and I look at all of them that are less than 0.505. Notice the ampersand here. So what this is going to give me, the stuff I'm highlighting right now, is a bunch of trues and falses. This part here is also giving me a bunch of trues and falses. If I put in an and there, I'm only going to get trues come back to me for those cases that have a 1 minus specificity between 0.495 and 0.505. I put that in an object called CK for check. I'm checking to see where this 0.5 is approximately. Okay? So just to show you. You see we have a few truths. Now with that then, what I can do is find what the corresponding sensitivities are for when I do have a 1 minus specificity between 0.495 and 0.505. And so what's going to be returned right here if I execute this code is just the cases where I have a true. There's the sensitivities. Similarly, for the 1 minus specificities, I get those. And I can also do that with my cutoff probabilities as well. I'm going to put this into a nice data frame, and this is what we get. So I'm looking to see where I have a 1 minus specificity of about 0.5. So we go right here. We go right here. What will be the corresponding cutoff probability? Well, about 0.709. And that's the cutoff probability that I would use. Notice what those sensitivities are over here, about 0.9. That's how you find the corresponding cutoff probability. It's definitely not, let's say, elegant, but that's the way it's done. Any questions about this? Again, think of my code as a template for your own code. So on a test, I might say, okay, suppose that the false positive rate's 0.2. What's the corresponding cutoff probability? Well, you take my code as a template, change a few things, and you get the answer. Now, there's a few other ways or a few other kinds of plots that you can do with the ROCR package. So, for example, suppose I again say plot save.perf, just like what we did before, and I add two arguments. One, colorize. It's going to add some nice color to the plot. But the second one's probably even more important for us. Print.cutoffs.at. It's going to actually print the cutoff probabilities on the plot. So if I execute the code, this is what I get for the plot now. So we can see before, when we were at 1 minus specificity of 0.5, we come up here. There was the 0.9. And look at, we have something called 0.7 there. That's the corresponding cutoff probability. So you could use this to approximate what the cutoff probability would be. I think my answer's, my way that I did before, is a little bit more precise. But that's how you could do it as well. So we can see that, so for example, a cutoff probability of 0.9 leads to a lower sensitivity, but a lower false positive rate. Think again, based upon what we talked about last time, why that makes sense. I'm going to have, with a cutoff probability of 0.9, a much higher threshold to overcome in order for me to say, yes, that place is going to be a success, or at least my prediction. And so because of that, you're going to be missing some place gates that were successes, because you have such a high threshold to overcome. Now we also see how this line is colorized as well. And it's kind of like if you've heard of like a heat map, this kind of gives you the corresponding, the color corresponds to what the cutoff probability would be. Now, one thing you've got to be very careful about, and I wish the authors wouldn't have drawn the plot like this, is that you might be thinking about, oh, this is a second y-axis there that gives me what the cutoff probability is. No, that is actually incorrect. So if I come across here at where it says 0.69, my cutoff probability is not 0.69. All this is like a legend. That's it. Where the color in the legend corresponds to the color that you see on the plot. So we can see how we're kind of a greenish yellow there at 0.7. Indeed, that's what we were right there. Okay, what are some other plots? Well, we could do an ROC curve for the validation data as well. So if you remember, pi.hat.v corresponds to the pi hats for the validation data. And so I use the exact same code that I had before, but I just put in the validation data. And this is my ROC curve right there. And if you compare this to what we had before, it's very similar. You can create other plots as well. Suppose I want to plot now my sensitivity on the y-axis still, but now on my x-axis, let's say I want to plot the cutoff probability. That might be helpful. So I could do that, do the plot, and this is what we get. So if you remember, when we had a cutoff probability of 0.7, come up, remember our sensitivity was about 0.9, and you can see that in that plot. So there are also situations out there where maybe you have more than one method that you want to use or that you want to examine to see which method correctly predicts the best. And we kind of talked about this before when I had a plot, if you remember here, and I said, well, what if we had something that looked like this as well? Which is the better method? Well, it was the red curve versus the purple curve. Okay? And so let's look at that in a little bit more detail. And we're going to go back to the place-kicking data set to do that. So one thing that we could do is look at the area underneath the curve. The method, the prediction method that has the most area can be considered the better method. Okay, so to find the area underneath the curve, what we could do is this. With the performance function, we simply say measure equal AUC for area underneath curve. And if I extract out y dot values from that, we just have one, and that area was 0.85. I could do the same thing with my validation data, and I get 0.839. And again, the curves are very similar. That's why we have very similar values there. Now, I'm not, perhaps I got ahead of myself by talking about making direct comparisons between two different diagnostic methods or two different prediction methods. Here, I'm just saying, okay, here's the area underneath the curve. This is first how you would do the calculation. Now, let's compare two different methods. Suppose we, in addition to the model that had all the variables in it, suppose we look at a model that has only distance in it. Suppose we have a model that only has elapsed 30 in it, which is the number of minutes elapsed in a half. So what I could do is estimate both of the models. So I have mod.fit.dist that only has distance in the model. I can find my corresponding pi hats. And then I could go through again the process to do what I need to do to get the ROC curve. Okay? Then for elapsed 30, I do the same thing, but now I just have elapsed 30 as the only independent variable. Go through the process to get the stuff that I need for the ROC curve, and then I do my plot. Okay. So, the first thing I'm going to do is take what I had originally with the model that has all the variables in it. We had saved the corresponding results in save.pref, or perf, I should say, and I plot it. I'm going to print the cutoffs at 0.3 to 0.9 by 0.1. So I'm getting a sequence of numbers from 0.3 to 0.9 by 0.1. And what that's going to do, let me actually go through those steps. And what that's going to do is give us essentially the plot that we had before. I decided not to include the colorization. Okay. Now I want to also plot on top of this what the ROC curve would be if I had just distance only. So I had saved those results in save.perf.dist. So again, I'm going to put some cutoff probabilities there. I'm going to make the color of the ROC curve to be red, and I'm going to add equal true to the code so that I add it to the current plot. And this is what I get. So now we can see we have the second ROC curve. I do the same thing now for the elapsed 30, but I make it blue, and then I add a nice little legend to the plot so we can distinguish between the three different curves. Okay. So here it is in my notes. So we can see elapsed 30 only does a much poorer job compared to the other two models. In fact, if we were to put the line of chance accuracy on the plot, we can see it's not that far above it. Now, if we compare the model that has all the variables versus distance only, we can see there's not much difference there. In a practical sense, they're given about the same results. And so because of that, I might say, well, maybe we should just use distance only. Now, from this plot, you can see, well, it looks like maybe the black line is above the red line a little bit more often than the red line above the black line. And so the black line is a little bit better. But in a practical sense, I don't think it's enough. And so what we could do now to compare the lines, or compare the curves, is find the area underneath the curve. And so I did that for my original model. I get that 0.8471 that we just saw about 5 minutes ago. And I can also do this with my distance-only model. I get 0.838. And so we can see that indeed it is a little bit lower. Look at the elapsed 30 model, just 0.56. That's it. Okay. Let's consider another situation. So 1 minus specificity. We have sensitivity here, 0, 0, 1, 1. So suppose I have a curve that looks like this. And I have a curve that looks like this. A cross. Which represents the better prediction method? It's not straightforward. This is now when, you could look at area underneath the curve, yes. But I wouldn't rely on that alone. It all comes down to, once again, for particular sensitivity, how much can you live with in terms of the false positive rate? That's how you would make the decision between these two methods. So on a test, what I've done before is actually given a plot like this, and I asked, well, how would you make a decision about which one to use? And so you would go through that logic that I just mentioned. Okay, so that's my discussion of ROC curves. Are there any questions? So we have one more topic to talk about, and that is something called complete separation. As I mentioned, I guess last week, logistic regression, to find these betas, the beta hats, we have to use a numerical iterative procedure to try to find it. And what happens with some numerical iterative procedures, it can't find what it's looking for. Okay? It's not going to be able, in our case, to find the maximum likelihood estimates. This can happen with logistic regression. The primary reason when it does happen is when something called complete separation occurs. Now, before we get to that, first of all, let's talk a little bit more about the iterative process. Now, by default, R will use 25 iterations to try to find what these maximum likelihood estimates are. Once it hits 25 and it hasn't felt as though convergence has occurred, it will stop and say, I don't have convergence. If that happens to you, probably the first thing that you should do, try to increase the number of iterations to see if by chance this will work. And there's an argument that you can use in the GLM function called maxit to do that. So if you say maxit equal 30, it will allow you to go up to 30 iterations. But if that doesn't work, you might be left with this situation of complete separation. What that basically means is this. Your independent variables completely separate out the y equals zeros, those observations, from the y equal ones. In other words, your independent variables have perfect accuracy in predicting y equal 1, y equals 0. One group actually had that happen to them already for their project. Okay? Now, when that happens, generally speaking, R will say it can't find the maximum likelihood estimates. And I'll explain why that occurs shortly. Also, another thing that can happen, R will actually sometimes say convergence has occurred, even if you have complete separation, even though convergence actually can never occur when you have complete separation. And if you start getting messages like this, fitted probabilities numerically 0 or 1 occur. This could be, and I emphasize could be a sign that you have complete separation. What often happens when you have complete separation, what will always happen when you have complete separation, is that your pi hats will either be 0 or 1. You'll see y coming up. So when you see a message like this, then you might be starting to worry a little bit. You can actually have this without having any problems at all. It could be simply, for some independent variables, you end up getting, for your observations, pi hats are close to 0 or 1. Okay? So to help show what complete separation is in a graphical context, let's look at the following situation. Suppose I have just one variable called x, one independent variable called x1. And when it is less than 6, y is always going to be 0. But when it's greater than 6, y will always be 1. So notice how x1 perfectly separates out the y equals 0s from the y equal 1s. It's completely separates them. So I form my data that has this situation. So I just came up with these 10 observations. I just made them up on my own. I have my x1, I have my y. And I estimate the model. And look what happens. It gets down to iteration 25. Uh-oh, we're having warning messages printed. Algorithm did not converge. Fitted probabilities, meaning our pi hats, are numerically very, very, very close to 0 or 1. You can still see what the beta hats are at your last iteration if you want to. And if you do that, and let's say plot the model, you get what's on the left side here. So I plotted the actual observations. You can see the code in my program. I plotted the actual observations, and I plotted the model using iteration 25's beta hats. Look what happens with the model. Notice how it's predicting the actual observations to have pi hats that are 0 or 1. But also take a look at the slope of this model here. Then in between where that complete separation, where that separation occurs. It's almost a vertical line. And so if I have almost a vertical line there, what's my slope approximately? Positive infinity. So I'm going up. So what happens with complete separations is false. The numerical iterative procedure is going to continue increasing beta hat 1 at each step of the iteration process. And it keeps on wanting to increase it more and more and more until it gets to positive infinity. Well, it can't ever get there. And so that's why convergence didn't occur. Hopefully from an intuitive standpoint, you see, okay, I understand why that slope is so great there. Because I see how the observations are separated like that. In maximum likelihood estimation, then simply it's going to try to find this line that's right between the 2 points that are closest to one another. It's going to try to really go up as quickly as possible. Now things get a little bit more complicated. Suppose I increase my number of iterations possible. If I do that, at iteration 26, with this particular data set, R tells me I have convergence. R has actually made a mistake. How it makes a decision about convergence, if you're interested, you can take a look at my textbook on categorical data analysis. I talk about that. How it makes the decision about convergence. Unfortunately, that decision process leads to this incorrect result. So you might be thinking, uh-oh, Chris, well, what can I do? You know, sometimes I might have complete separation here. I have a problem, but I didn't actually have convergence. Of course, we don't want to use a model that doesn't have convergence because the beta hats will, if I could continue the iterative process, will continue to change. And so that's where you have to fall back on this particular situation here. Your fitted probabilities are numerically close to 0 or close to 1. Again, take a look at this plot. We can see why that should occur when you have complete separation. So when that warning message comes about, It does not mean you have complete separation, but it's a sign that that could be happening. What you could do to continue to follow up on, do I have complete separation or not? This is explained later. In this note, take a look at your parameter estimates. Take a look at the corresponding standard errors, the square root to the estimated variance of those parameter estimates. If those are getting really, really big, that's a sign that indeed complete separation has occurred. Now, why should that matter? Well, at least with respect to the regression parameter estimates, the beta hats, hopefully that will make sense. Because if we come back to this plot here, you know, in order for pi hat, let me actually write it out. In order for pi hat to be close, very, very close to 1, or very, very close to 0, what are the beta hats going to have to be? Either very, very large or very, very small. That's why you have, let's say, large beta hats, in an absolute value manner. So you can have, let's say, negative 1,000, whatever, for a beta hat, or positive 1,000. In order to get this to be close to 0, you're going to need these parameter estimates to be very large or very, very small. And so if you're seeing that happen, then you'd be thinking, and you have these warning messages pop up, you should be concerned if you have complete separation. Now, interestingly, if I were to just change two observations here, so I move this 5 to 6, I move this 6 to, 5, I get this curve, and I no longer have the curve. I no longer have complete separation. So, what are some possibilities of what you can do with complete separation when it happens? There are other ways that you can estimate logistic regression models. And, we simply just don't have the time to talk about all those other methods. Complete separation occurs, but it doesn't occur that often. So that's why I don't go into the details, but here are two possibilities that you can do. One in particular, I'll just mention, you can modify the likelihood function. So we've seen the likelihood function before, and what you can do is put an additional part to it. Let's say at the very end of the log likelihood function, that actually is a penalty. It's a penalty for having, let's say, beta hats that are too large or too small, or let's say, too large in absolute value. That penalty will allow you to now do reach convergence. Again, this is talked about in my categorical book if you're interested. An additional comment, well, complete separation is not necessarily a bad thing if our only goal is prediction. Because what this is saying is that you can use your independent variables to perfectly predict the y equal 1s from the y equal 0s. So in that context, that's not a bad thing. It's just you're not going to be able to state your logistic regression model because if you continue your number of iterations, your beta hats are changing. These beta hats are used for interpreting your model. So that's why that's a problem. Okay, we are out of time here. So let me come back over here to these notes. So what's next in our class? Of course, I have my usual office hours. Thursday, of course, we don't have class because of Thanksgiving. Next Tuesday, we will start a new section, multinomial regression, which allows us to extend logistic regression from, let's say, having just 2 groupings to now, let's say, having 3 groupings, or 4 groupings, or 5 groupings. We will discuss the grading of project number 3. We will review for the tests. Our test, then, is the following Thursday. So please come prepared to bring questions if you do have them. So again, project number 3 is due at 5 p.m. today. Are there any questions? Okay, that's all then.